Hello everybody, today I'm going to be showing you a few seemingly unrelated fun facts about Pascal's triangle. Okay, and I almost forgot what I was going to be talking about. So, first question is, what is Pascal's triangle? Well, it's better to just show ya. So let's say you start with the number 1 at the top, and there's a bunch of zeros. It's a row of 1 and a bunch of zeros. And then, between the two zeros, you add up the two elements, two numbers that are above you. So 1 plus 0 is 1, and likewise on the other side. Then you continue that. There's zeros all along here because we did 0 plus 0 to get those. And you would get, do the sum of 1 and 0, you would get 1. The sum of 1 and 1, so you get a different number now, 2. And you get this number here, 1. So you can see it's symmetrical, and I'm just going to fill out a few of the numbers now. So 6, 4, 1, and as you can see, you can just do this forever. So 10, 10, 5, 1. Okay, maybe that doesn't seem too interesting. I mean, it's a triangle, you know. There's not a whole lot to it. What's so special about this triangle? Well, you may have been introduced to it in one way, but I'm not, which is with binomials, but I'm not going to cover that one first. I will in a minute, okay? So we got this structure. So here's a question. What happens if I colored in all of the odd numbers? So I'm just going to circle all the odd numbers or something like that, like this. One, none of those are odd. 1, 5, 5, 1. Okay, and we continue in this pattern. But there's a better way of doing it. Don't use big numbers if you don't have to. So here's the other way of doing it, which would be easier to compute in your head. But basically, you start with a 1 on the top. And one fact that we know about even numbers is that if we divide them by 2, we get a remainder. And if the remainder is 1, then it's an odd number. And if the remainder is 0, then it's an even number. So we'll just write a 0 for when it's for when the remainder is 0, which means it's an even number. And this is actually just like adding in binary, basically. If you do 1 plus 0 in binary, you get 1. If you do same thing on this side, but if you do 1 plus 1, we get 2, which is 1, 0 in binary. So we're going to restrict the amount of digits in our number, and we're just going to get the last number. And for any binary number, the last bit, the least significant bit, tells you whether it's odd or even. Anyway, so let's just, I'll just show you, okay? So, in this case, 1 plus 1 is 2, but we're just going to make it 0 because 2 is even, okay? And then 1 plus 1, or 1 plus 0, I meant to say, is 1, and we get this shape. So 1, 1, 1, 1, 1, 0, 0, 0, 1. And so just in case, hopefully you have noticed the pattern by now, but if we're adding 1 and 1, we get 0. If we're adding a 0 and a 1, we get 1. If we add two zeros together, which I haven't done yet, we get 0 as well, okay? So 1, 0, blah, blah, blah. I'm just going to continue this pattern here. 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1. I think I'm almost done. This is the last row that I will do. So I'm just putting them between each number. 1, 1, 1. So maybe you can see some kind of pretty structure here. I certainly do. And I found out about this by watching a mythology video. Not gonna act like I figured this out myself. I did try and figure out how to draw what I'm about to show you using just like pixels and stuff like that in my shaders. But if I just draw lines through all the ones, we get this sort of shape. And if I continue this, and I used pixels, and I colored in the pixels like this, and I did that instead, then what kind of shape would I get if I just continued this forever? Well, you would get the Sierpinski triangle. What is the Sierpinski triangle? It's a fun little triangle made of other little triangles, made of other little triangles. So you start with the big triangle, or this is one way of doing it. You could do it using Pascal's triangle, which we just found out. You could start with the big triangle and subdivide it into 4 other equilateral triangles. They don't have to be equilateral, but as long as it's even shape. Then we just get these 3, the 3 of those 4, and do the same thing to those. And we just continue this recursively. So for each triangle, we draw a little triangle here. And we could just stop at some point and color in all the triangles that we have gotten. And you would get this cool fractal shape, which is the Sierpinski triangle. And you can do it with Pascal's triangle. So that is fact number 1. I definitely think I should have made the whiteboard on my left side because that's better. Let's just adjust the camera real quick because it's making it pretty hard for me to write here. Just move this table over a little bit. Okay, so that's better. That was fact number 1 or 2 or whatever. Here we go. Next fact. Let's say we have something like in the form of a plus b to the power of n. And n is just some integer, and they're just some real numbers. Okay, so I don't know. They could be anything. What happens if you expand this? Well, let's start with expanding it with the power of 2. If we do that, basically we use FOIL or whatever you want to call it. You're going to multiply every single number. It's going to expand to something like this. It's a plus b times a plus b. And if we expand that out and we multiply through, we do a times a plus a times b plus b times a plus b times b. Okay, so what do we end up getting? We end up getting something that looks like this. A squared plus 2ab plus b squared. Okay, that's pretty boring. You might remember that from high school. But what if we used a higher power? Let's say 3. And I could use this this long method of trying to expand it and figure it out myself, but there's a trick. And I'm just going to write down what happens if you put it to the power of 3 first, expand it, and then I'll explain how I was able to do that. So, wait a second. 1, 3, a squared b plus 3 a b squared plus b cubed. Okay, so yeah, how was I able to expand a plus b times a plus b times a plus b? Because I'm not a math whiz, or I'm not good at doing little calculations. But there is a trick. The trick is these coefficients that we're getting in front of here. In this case, it's a 1, and here's a 2, and here we have a 1. That's 1, 2, 1. I actually failed to see the pattern here. 1, 3, 3. What the hell? 1, 3, 3, 1. That's not Pascal's triangle, is it? Oh, I'm missing this layer. You start at 1. Okay. So the coefficients for A and B is 1 and 1. And the coefficients for this one is 1, 2, and 1. 1, 2, 1. And the coefficients for the expanded to the third power is 1, 3, 3, 1. So this would be like to the 0th power. This would be like to the 1st power, 2nd power, 3rd power. And you could just continue doing that. And then these other parts, you could probably see a pattern. It's like A cubed, A squared, A, no A. And same if you go from the other side. B cubed, B squared, B, no B. Okay? So that's interesting. It's a fun little way, or it's a good way, easy way of calculating, figuring out what the coefficient should be when you expand A plus B to the power of any large number. You can figure out the coefficients like that. Fun fact, number 3. Okay, I'm not sure how I should frame this one, but we'll do it this way. Let's say we have 5 cards. So we have 5 cards, and we want to ask the question, how many ways are there of choosing 2 cards from these 5 cards? Well, we could choose, we could choose this one and this one. We could choose this one and this one, this one and this one, this one and this one. Or we could choose this one and this one, this one and this one, this one and this one, or this one and this one, this one and this one, or this one and that one. So how many was that? Well, the answer can be solved by a formula, which I will not explain, but it is written in math terms as just 5 choose 2. And what is 5 choose 2? Well, in this case, I think it's, first we drew 1, 2, 3, 4 connections, and then we drew 3 connections, and then we did 2, and then 1. So 4, 3, 2, 1. So we just have to add those together. 3 plus 2 plus 1 is 6, plus 4 is 10. So 5 choose 2 is equal to 10. Okay? And what happens, okay, we want to see what's the behavior of this when we choose any value for n, any number of elements, and choose any value for what we'll call k, which is the number of things that you choose. Okay? So, like, what happens if you have... dang it. What happens, how many different ways are there of choosing 0 things from 3 things? Well, there's 1 way. And how many different ways are there of choosing 1 thing from 3 things? Well, you could pick 3 things. So there are 3 different ways. Okay. And then we'll do 3 choose 2. How many different ways are there of choosing 2? Well, this is interesting because we know that the number of ways of choosing 2 things from 3 is the same number of ways of choosing 1 thing from 3. Because you could think of it as, you're thinking you can pick 1 thing. There's 1 of the 3 cards because we're choosing 2 cards. The number of ways of choosing 2 cards is the number of ways that you can exclude a card from your choosing. So in this case, if we exclude 1 card, then there would be 2 here. And there's 3 different ways of excluding a card. And so then there are 3 different ways to choose 2 things from 3 things. And similar reasoning as what I just did there. 3 choose 3. Well, there's only 1 way of choosing 3 things from 3 things, and that is 1. So we get this symmetrical thing here. And what we might notice, this is one of the rows of Pascal's triangle. 3, 3, 1. And what's on top? 1, 2, 1. And so this is actually telling us how to choose different amounts of things from 2 things. If you choose 0 things from 2 cards, if you choose 0 cards out of 2, then there's 1 way of doing that. If you choose 1 card out of 2, there's 2 ways of doing that. And if you choose 2 cards out of 2, there's only 2 ways of doing that. This is maybe uninteresting for small numbers, but you might be able to, you can draw Pascal's triangle pretty quick and be able to do it for slightly larger numbers, like 4, 6, 4, and 1, and 1, 5, 10, and 5, and 1. And this 10 here, is the first one we did, where this is 5, choose 2. So the way you would you'd be able to use this triangle to calculate choosing formula. So that's pretty cool. And choosing formula is very useful for doing like probabilities and stuff like that. So you can figure out how many different ways are there of something happening. So if you're playing poker, you can figure out how many different ways, how many hands you could have, or how many ways are there of getting a flush, and how many total different hands you could get. And just compare those and get a probability of getting a flush, which seems pretty helpful if you're trying to win. So let's get to the next fact. This is one I actually just figured out recently, and it sort of surprised me, but I guess it wasn't that crazy. I should have seen it coming for sure, because I was thinking about choosing things and stuff like that. But here's the question. Let's say you're a person. Maybe I'll just put away the pen right now because I don't really know how to draw this. But let's say you're a dude, and or a female. I don't know what woman. Anyway, and you start here, and every second, every unit time, you decide to step a unit step left or right. You never decide to not step. You're always going to step some direction, but you pick a random direction which you're going to step. And I'm going to step this way. And in the next second, I'm like, okay, I could either step this way or the other way. And basically, what happens if I just keep on doing this stepping thing, where I step left or right by 1 unit? How am I gonna, what's the likelihood of me being somewhere, given a certain amount of time has passed? I can't, because you could just go back and forth every second, or you could just take right every step. So there's all these different paths that you could take, and sometimes, there's more than one way of getting somewhere. I could get back to the start by going right and then left, or I could have gone left and then right. So how many different ways are there of, doing that? Well, here's how I figured it out. But basically I drew a grid, and this is the messy part. Hopefully we'll get the pattern before we need to draw too much of it. Let's start here. So we start here. There's one way of us getting there. Let's draw zeros everywhere else. I'm kind of giving it away, aren't I? In the next step, the number of ways of getting here, there's only 0 ways of getting there, because, so this is like time is equal to 0 time 1 time 2 times 3 and times 4. And I said that every step in time you had to go left or you had to go right. You never decided to just sit still. I'd like to see what would happen if I did that. I think it would be similar, but slightly different. But yeah, if you had to go left or right, then you might end up here, you might end up here, and there's no chance of you ending up there or there or there or there. In the next step, you could, if you were over here, you could go over here, and if you're over here, you could go over here. But if you're over here, you could also get here. So actually, there's 2 different ways of getting here. So we'll put a 2 there, because there's a higher probability that you're going to be there, which makes sense. It's somewhere along where you started, and you're moving backwards and forwards randomly, or sideways randomly. So it makes sense that there's 2 ways of getting there. You're more likely to end up there. And we continue this pattern. There's 1 way to get here, and there's how many ways are there of getting here? And actually, this is when I realized that it was just Pascal's triangle at this exact point in the step, because I was like, okay, well, there's two ways of getting here, so therefore there's two ways of getting here, plus the one way of getting there from also this side. So you could have gone like this, 1, 2, or 3. So there was 3 different ways of getting there, and it's symmetrical, so you don't really have to draw both sides, but I'll do it for completeness sake. And as we can see, the shape that you get here is just Pascal's triangle here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on and so forth. So like 4, 6, you know. I don't need to draw Pascal's triangle for you again. So that's called the random walk. And I got thinking about that because in my astronomy class, and I had already heard of it before, but in astronomy class they said when a photon is created in the center of the sun, it takes a random walk. I mean, the photon doesn't prefer to leave the sun. It's just strolling through, and it's bouncing off all the particles, which are the center of the sun is very dense, and so it's bouncing off all the particles, and eventually it gets out. But how long does it take to get out? Turns out it takes about 1 million years, and so it sort of takes a random walk. That must be something like that. Which brings me to fact number 4. I lost count. What happens if you graph the bottom shape of the triangle? So I'm just gonna draw the triangle again, and I'm gonna draw it small so I can fit in a lot. Okay, like this. 1, 4, 6. I'm still making mistakes. 1. Maybe I should just draw half. 1, 5, 10, 1, 6. I'll draw the whole thing. 5, 10, 10, 5, 1, 15. We never gotten this far. 20, 15, 6, 1, 1, 7, 21, 15 plus that is 35. I hope I do that right. I'm pretty bad at like doing quick math. That's 21 again. 6 plus 1 is 7, 1, and maybe this will be our last row. 1, 8, 28, 21 plus 35, what is it? 56. 35 plus 35 is 70. 56, 28, and 8, and 1. And you know what? I'm going to go for one more. Why not? 1, 9, 36, 28 plus 56. Okay, I'm really bad at math. 70 plus 14 is 84. And 70 plus 56 is, let's draw commas between these so we can maybe separate them. 70 plus 56 is 126. So 126. Hey, I wrote 65 here. That's supposed to be 56. Man, I really messed up. Okay. And we don't need to complete it, but I will. Okay. So 126 again. 84. This time I'm going to copy the numbers from the other side properly. 36, 9, and 1. So, what happens if you draw this curve? Sorry, I'm kind of giving it away. But either way, what happens if you graph this such that this is the x-axis and the height of the graph is the number, okay? So we'd start off at 1. Let's draw it really far down there. Start off at 1, and then we'd go up to 9. Then we'd go up to 4 times that amount, so 36. And we'd go up to about double that amount, 84. Then we'd go about to almost double. I'm just going to draw it. I'll just overlap it. Okay. So we get this shape. Do. And it seems to, does it grow faster? It starts growing faster over here. Then the rate that it grows, see the difference in these numbers is getting smaller, or the factor's not the same as the distance. Anyway, point is you get that, and since it's symmetrical, you get that. And what is that? Well, I don't know. It looks kind of like a bell curve to me. Turns out in statistics they use a lot of approximations of this shape because calculating this for very large numbers can get pretty out of hand, if you could imagine, because these numbers start to grow pretty fast. And yeah, but you get this cool curve here, and I think it's the normal distribution. Honestly, I don't know. I've been trying to find somebody who could explain this to me, because I want to know why it happens to be this nice curve when you graph a certain row of the binomial or of the Pascal's triangle. So what is up with that? Same thing you'd get. Lastly, this is pretty much the same thing. You may have noticed there's probably a pattern obviously here. I am talking about Pascal's triangle after all, but I'm talking about different ways you can apply it or different places you can see Pascal's triangle. One of the ways is like if you have a box of coins. Let's say you have a box of 100 coins, and you get the box and you shake it, ba, 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 and you figure how many different ways are there of getting half of them, or actually, better question maybe, what's the probability that half of them turn up heads and half of them turn up tails? Well, surely it's higher than the probability that all of them turn up tails. That seems pretty wildly unlikely. And the reason why that is because there's more ways for half of them to turn up heads, or like half of them to turn up tails. So yeah, there's more ways. So the way you could calculate that is maybe using the choose formula. You just choose 50 out of 100. So you do 100 choose 50, and the number that you get there is probably huge, and I'm not going to write it out. I'll just write huge. But the number of ways that you could choose one thing from 100 is only... Oh, I shouldn't use my finger, I'll get it all greasy. The number of ways that you could choose one thing from 100 is just 100. So 100 compared to huge, is pretty small. And again, if you were to graph this for different, the probability of getting different amounts, so like the probability of getting 50 would be here, 25 would be here, and 0 heads would be here. Otherwise, you could get 100 heads, or you could get 75 heads. And if you graph the probability, you'd get a peak at 50, and go down like that. And you could also, like I said, you could get this by doing Pascal's triangle, and with the height of 100, and then graphing all those little numbers. So this is actually like discrete. A shape like this. But often what's interesting is that we see this shape and it looks continuous in nature, because if this number is extremely large, in this case it's 100, so we're already starting to approximate a pretty smooth shape. But if this number is absolutely bonkers huge, then the number of ways of, like if you had 1 billion atoms and you had to choose 500 million from them, that number is astronomical. That number is probably way larger than the number of particles in the universe. There's just so many ways that something could happen. And that's why this is interesting, doing this choose type of thing, because you can calculate how many different ways can something happen. And I think that concludes this video. Thank you for watching if you got this far. Comment, like, subscribe, something like that. And hopefully I'll actually post this on my YouTube channel, because sometimes I just record videos and don't post them because I'm too lazy. So, yeah. Have a good one.